So anyway, since it's been a while since we've had class, I want to do a little bit of review. Let's do something like this, where this is 9 foot 10 inches by 15 feet 8 inches. I want to find the perimeter. How do we find the perimeter of a rectangle? Add up the sides. Perimeter is distance around.
Oh, you add up all four sides.
You got it. So we have actually two different possibilities here. Possibility one, we can do exactly what you guys just said, add up all sides. And we can do this all at once if we want to. We've got the 15 foot 8 inches, 9 foot 10 inches, 15 foot 8 inches, and 9 foot 10 inches again. And we can just add all those up. 8 and 10 make 18 plus another 8. 26 plus 10, 36. Well, 36 inches is more than a foot. In fact, it's exactly 3 feet. So there's 0 inches here, and we'll carry the 3 feet. 3 and 15 make 18 plus 9, 27 plus another 15. 42 plus another 9, 51. So that's exactly 51 feet is that perimeter. The other way we could do it, there is a formula for perimeter for a rectangle that the perimeter is 2 times the length plus 2 times the width. Now, we really haven't gone over using formulas like that yet, but we could simply take the length of 15 foot 8 inches, multiply by 2. What's 2 times 8? 16 inches. Of course, that's more than a foot. That's 1 foot with how many inches left? 4. Good. So keep the 4 inches and carry the 1 foot. 2 times 15, 30 plus 1, 31 feet. So that's 31 foot 4. Then we also do the width times 2. 9 foot 10 inches times 2. 2 times 10, 20 inches. Of course, that's more than a foot. That's 1 foot with how much left over? 8 inches. So we'll keep the 8 inches, carry the 1 foot. 2 times 9, 18 plus the 1, 19 foot. And now we do have to add those two together. So 31 foot 4, 19.8. Yeah. Hopefully it turns out to be the same number. 4 and 8 do make 12 inches, which of course is exactly 1 foot. So we've got 0 inches, carry the 1 foot. 1 and 31 makes 32 plus 19 is 51. Perfect. Let's go with a slightly more difficult problem. We're going to find the length of trim needed. Pretend that looks like a half circle. This diameter is 6 feet 8 inches. So we're going to find the length of trim needed to go around that whole window. We're going to add 2.5 inches for each miter. And we're going to give the answer in feet, inches, and sixteenths. So again, pretend that's a half circle. We need to find the distance around it. Well, to find the distance around the round part, we're going to pretend it's a full circle. If it were a full circle, how would we find the circumference of that circle? Pi times diameter, yeah. Well, here the diameter is 6 foot 8. When we multiply times something like pi, we don't like having it in dual units. We want to turn it either all into feet or all into inches. So it's a lot easier probably to turn it all into inches. So 6 feet 8 inches is going to be how many inches? Well, 6 times what? 12 is 72 plus the 8, 80 inches. So that circumference is going to be pi times 80 inches. Pi times 80 inches is what? 251.2, I believe, inches. But we only want this much of it. So what do we have to do? Divide by 2. Good. We divide that by 2 to get 125.6 inches. So that's the highlighted part. What more do we still need? That part. How much is that? 80 inches. So we add 80 inches to that. That's 205.6 inches. Now we have this little piece here. Add 2.5 inches for each miter cut. How many miter cuts have to be made? Careful.
1.
Coming from this way, there's a miter. Coming from that way, there's a miter cut, right? So there's going to be 4. Each corner is 2 miter cuts because both pieces have to be mitered to fit together. So that's going to be 2.5 inches times 4, which is how much? Careful. 10. There you go. So we have to add 10 inches to that. So we add 10 inches to that, we get 215.6 inches. Good. Now I want that in feet, inches, and sixteenths. So if I have my calculator going here, let's get back here. If I have 215.6 in my calculator, that's in inches. How do I turn it into feet? Divide by 12. So that's 17 feet. What do I do here now? Subtract the 17 whole feet. Then, careful, I gotta get it back to inches yet. Multiply by 12, 11.6, that's 11 inches. Now what? Subtract the 11 that we used up, and then the 0.6. Now it's not divide, but multiply by 16. To see how many sixteenths. 9.6, which is 10 sixteenths, or 5/8 inches. So that'll be 17 feet, 11 and 5/8 inches. That one, yeah, takes some effort. Let's have you convert 7 3/4 feet into inches. We've done a lot of whole numbers. We haven't done a whole lot with decimals and fractions yet for conversions. Perfect. Yeah, you're just going to basically end up multiplying it by 12. I'll write up the full conversion just so you have it. But yeah, 7 3/4 times 12. You're close. That's 7 1/4 times 12 would be 87. 7 3/4, what would that be as a decimal? 7.75. So if you had to, you could just do that. 7.75 times 12. Should be 91. Nope, 93, sorry. 93 inches. We've done a couple of examples of this, but let's run through them all again here quick. 4 feet 8 inches plus 9 feet 11 inches. What do I do first? Inches. 8 inches plus 11 is 19. Of course, that's bigger than a foot. It's 1 foot with how many inches left? 7. So we keep the 7 inches and carry the 1 foot. 1, 4, and 9. 14 feet. So 14 feet, 7 inches. So we might have 8 foot 2 inches minus 4 feet 11 inches. We're going to have to borrow. So this will be 7 feet. This is going to be 14. Good. 14 minus 11, 3 inches. 7 minus 4, 3 feet. So 3 feet 3 inches. If I have 3 feet 8 inches times 8. 8 times 8 inches is 64 inches. Of course, that's bigger than a foot. How many feet? 6 times 12 would be 72. 5 feet. How many inches would be left? Well, 5 times 12 would be 60. So there's 4 inches left. We carry the 5 feet. So that's something you can always do. You get the 5.3333333. You got to remember that's feet. So it has to go back to inches then. So now 8 times 3 is 24 plus the 5, 29 feet, 4 inches. It looks a little strange written like this, 9 feet 8 inches divided by 4. But we can change that up to be a little more familiar by writing it like this. Now 4 goes into 9. How many times? 2. 2 feet. 2 feet times 4 is 8 feet. Subtracting gives us 1 foot. Now before we bring down the 8 inches, we have to turn that 1 foot into how many inches? 12. Now I bring down the 8 inches, we have 20 inches. Good. And then 20 inches divided by 4, 5 inches. 2 feet 5 inches. So let's convert 4.29 feet to inches to the nearest eighth inch. So 4.29 feet. To turn that into inches, what are we going to do? Times 12. You got it. So we'll start out with the calculator. 4.29 times 12. So that's how many inches? 51. Now to the nearest eighth, how do I make that into the nearest eighth inches? Well, first, I subtract the 51 whole inches, and then nearest eighth, so it's only going to be times 8. Yeah, if we're going to the 16th, it would be times 16. So 4 eighths or half inch. What do you think? Good stuff? Okay. So we do have a quiz coming at you since it's been, 2 weeks since we had one. There you go, extra protein.
Yeah. Got some.
So our new topic for today, we're going to start working with basic area. And basic area is derived, well, everything in geometry is derived from the most basic concept. In geometry, that most basic concept is that thing right there. It's just a location. It's called a point. We can create a length, or what we call a line segment. In practice, we probably just call it a line. We often just call it a line because there aren't any true line segments in reality. And we do that by just taking that point and we drag it in a single direction. The length of that segment is just equal to the distance that we move the point. Now, if we take that line segment and we drag it in a second direction, think of taking a stick and like dragging it across the stand or sawdust or whatever. It's going to trace out a shape. It's going to be a rectangle. But just like the important dimension of the line segment was its length, the important dimension of the rectangle is an area. And the size of that area depends on what the length of the original rectangle was, or the original line segment was, times that distance that we moved. This time that distance moved is what we often refer to as the width. So the area of a rectangle is a width, length times a width, or width times a length, whichever order you want to put them in. But it's more important than that. It's important that we note that that width is always what we call perpendicular or at a right angle to that length. Because every area has to be calculated from perpendicular dimensions. So if I just have a rectangle, pretend those look like right angles, that's 8 feet by 18 feet. How do I find the area of that? Length times width. 18 feet times 8 feet. So 18 times 8 is going to be 144. And then we also, remember when we also multiply the names. Feet times feet, feet squared, square feet. Perfect. But it doesn't have to be a perfect rectangle. We mentioned that the length and the width just have to be perpendicular at right angles. The reason for that is if I take this rectangle and cut it up into really thin slices, you can almost picture it as like a stack of papers. What I have here is a bunch of really thin rectangles. And if I push that and just kind of tilt it, what I'll get is a bunch of rectangles that are slightly offset. I'm not going to keep drawing them all out, but looks like that. This length here is still going to be 18 feet. This height here is still just the total thickness of all these rectangles put together, correct? Has that changed? No, it's still 8 feet. The area of the end of this has not changed. We've just slid it over. So the area of that is still the 18 feet times the 8 feet, or 144 square feet. So this shape here is what's called a parallelogram. And the area of the parallelogram, just like the area of a rectangle, is a length times a width, as long as that width is taken at a right angle like that. Now you might say, well, that doesn't look much like a rectangle. It actually is. It is simply a, come on, huge delay on my computer today. Yeah, if I just cut this triangle off the end over here and put it over here, well, we now have a rectangle. And it makes sense. That's just the length times the width. In fact, if we think of that idea of taking that line segment or that stick and dragging it across the stand, if I have an 18-foot stick, I know that's a long stick, but I don't even have to drag it straight. As long as I keep it parallel to its original orientation, I can drag it like that if I want to. This is still 18 feet because the length of my stick hasn't changed. And if the distance I dragged it is still 8 feet, well, guess what? The area is still 18 feet by 8 feet. 144 square feet, yeah. Again, it's because this is just a rectangle. If I come back here some distance, it really doesn't matter where. If I cut this piece off and I move it over here, it'll exactly fit in over here to make, again, a rectangle. So all those weird shapes can be brought back to a rectangle. So then let's look at one that's not a rectangle, a triangle. Now this is what we call a right triangle, of course, because it has a right angle in it. But the more important part is that in a right triangle, it's really easy to find something that's called the related rectangle. The related rectangle, of course, is just that. How does the area of that triangle relate to the related rectangle? It's divided in half, exactly. So if this is still 18 feet by 8 feet, the area of that triangle is just 18 feet times, oops, not squared. 18 feet times 8 feet divided by 2 or times 1/2, however you want it. Yeah, it is 72 square feet, half of the 144. It's easy to see in a right triangle like that. It is less easy to see in a triangle that is not a right triangle. So if we look at something like this, let's say this now is a 15-inch bottom base down here. The related rectangle is going to look like this. Well, the 15 is the length of that related rectangle. We often refer to that as the base of the triangle. The base is just any side of the triangle that we know the length of. But we also need to know the width of that related rectangle, and that dimension is going to involve the third vertex of the triangle. The first two vertices or corners of the triangle are part of that base. There's only one vertex or one corner that's not part of the base, and that's this one up here. So the distance from that third corner to the base, distance is always measured at a right angle, like that. That distance is our width. Well, that distance is called the height of the triangle, or sometimes called the actual line itself or line segment itself is called an altitude. So let's say that distance is 12 inches. The area of this is 15 inches times 12 inches. That would be the area of the related rectangle. To get the triangle, we divide by 2. So 15 times 12 is 180, divided by 2 is 90 square inches. The one that's a little trickier to see is a triangle that looks like this. An obtuse triangle, yes. So let's put a dimension down here. Let's call this 14 feet from there to there. Well, I am going to make 3 rectangles and 3 sets of triangles. My first triangle is that big black triangle there. And what I'm going to do is I'm going to make a gray rectangle that encloses all of that. I'm going to move that off to the side. Of course, half of that gray rectangle is like that. If that's more than this, that black triangle there is more than the main one that I have here, right? You can see that it has this piece in it. So the extra piece is this piece right here, the blue. Well, that blue, if I move it over here, is part of that related rectangle. So I have the blue rectangle like that. I have the gray rectangle, come on, out here. Well, we'll need a third rectangle. Let's put a green one in here for this. Excuse me. So if we look at that, that green rectangle minus plus the dark blue one gives us the big gray one, right? Well, half of that green rectangle, I'm missing what I want to say here. Anyway, so gray minus green equals blue, or gray minus blue equals green, however you want to look at it. I want to show that that green rectangle is actually the related rectangle for this black triangle. And the way that we do that is this black triangle minus this light blue one gives us that original triangle that we have in there. So that green rectangle here is the related rectangle. So the height of that green rectangle is found from, again, the third vertex. But if we go at a right angle, it doesn't hit the base, the original side. So we have to have our altitude way off to the side. So I went the long way about saying that. I did a poor job of explaining that. But the altitude is outside of the triangle. So let's look at this. Let's say that is 9 feet. So the area of that triangle is still 14 feet times 9 feet and divided by 2, giving us 63 square feet. Well, there are other shapes that we want to find the areas of. The big one is a circle. Well, for a circle, there's only one really defining characteristic. That's the radius. Everything else about the circle can be found from the radius. Like the diameter is just twice the radius, right? So diameter equals 2 times the radius. Well, one of the characteristics of a circle is the distance around the circle, the circumference. What's the formula for the circumference of a circle? Pi times the diameter, right? Well, the diameter is 2 times the radius. So I can write that off as, come on. Yeah. 2 times radius times pi, or 2 times pi times radius. The order doesn't matter. When we multiply, we can change the order of the numbers. So what that means is if I just want half the circle, that distance is half of this. Well, if I divide that by 2, that distance, the 2's just divide out, that distance is just pi times radius. Make sense? So I'm going to take that half circle, I'm going to cut it into really thin pi wedges, really thin little triangles like that. Then I'm going to fan them out. And I get basically like a comb here with really fine teeth. It does, kind of, doesn't it? Yeah. That's kind of fitting for math, isn't it? So now this dimension here is just the radius of the circle. This dimension here, if I cut those thin enough, is just that half of the circumference, or pi times the radius. Well, I still have half a circle left, so I'm going to cut up that other half a circle in equally thin slices, fan them out, and slide them in. They should fit in exactly into these spaces that were between the teeth of the first piece, right? That is now pretty much, if I cut them thin enough, a rectangle. The length is pi times radius. The width is the radius. So the area is pi times radius, or pi times radius squared. Hopefully that's the formula you've all seen before for the area of a circle. Now with that, what's that? Yeah. Now with that said, we're not going to do anything fancy like this. We're just going to use the formula. If I have a circle with a radius of 4 inches, the area will be pi times 4 squared. If I use 3.14 for pi, that comes out to be, 50.24 inches squared, about? You should. I'm wrong a lot, especially, what's that? Close enough? I got to check it out. 50.24 is correct. If you use the pi key, now most of your calculators have a pi key. If you use the pi key, it comes out to like 50.26 because I'm using just 3.14. And so it's a little bit different. On a quiz or a test, what I usually do is I do both. I use 3.14 and then I use the pi key. And then any answer in between those two numbers is okay. So how about for this circle here where I've got a diameter of 10 inches? How do I find its area? It's pi times radius. Radius squared. What's the radius here? 5. Good. Yeah, there's a lot of subtleties to these. Pi times 5 squared, that was like 78.5, I believe, square inches. Not so bad. Who can tell me what a trapezoid is? What's that? Search it up. Looks like half an octagon. That's exactly right. It's a four-sided figure. That trapezoid has 4 sides. I drew this one a little lopsided, but if it's a regular trapezoid, it is usually basically half an octagon. Kind of like half an octagon. It's got 4 sides and 2 are parallel. So the 2 sides that are parallel, here it's the 2 that I'm going to put in blue here. Those are called bases. So I'm going to label the small one with a little b, the big one with a big B. And then the distance between those bases is called a height. Now, I'm going to label that with just an H, but I want to make a note here. This idea of a height being the distance between 2 bases is a common theme when we talk about geometry. We are used to height as being from the ground up or a vertical dimension. In geometry, it's not necessarily a vertical dimension. It is often, like we said here, the distance between 2 bases. We'll look at more examples of that before we're done here. So to find the area of that trapezoid, I want to try to make it into a rectangle. So what I'm going to do is I'm going to go halfway down this sloped surface here, right there, and I'm going to cut that off square. Well, this little piece here, if I flip it up, exactly fits into there. I'll do the same on the other side. Go halfway down, cut that off square, flip up that little piece there. Well, now I have made a rectangle. The height of that rectangle is still just the original height of the trapezoid. The length of that rectangle is now bigger than the small base and smaller than the big base. It's somewhere between them. It's actually exactly between them. It is the average of those 2 bases. So the area of a trapezoid has a length that's the average of the 2 bases, so little b plus big B over 2, and then times that height is the width of the related rectangle. So let's put some numbers in this. Oh, let's call this 28 inches. Let's call this one 42 inches. And give this distance across here 15 inches. So the area, what are my two bases? 42 and 28. So I add them together and divide by 2 times my height of 15. So what is 42 plus 28? 70. 70 divided by 2? 35. And 35 times 15? 525. Those units are in inches, so it is square inches. So here again, this time the height was still vertical, but it doesn't have to be. Remember, the bases are the two sides that are parallel. That's a trapezoid. Those purple sides are the bases. So let's say that this is 8 feet here. Let's call this one 26 feet. The height is the distance between the bases. I actually do have to extend this to get that height. Let's call that, well, let's go 14 feet. So to find the area of this, what are my two bases? 8 and 26. So 8 plus 26 divided by 2, and then times 14. Well, 8 plus 26 is 34. 34 divided by 2? 17. And 17 times 14? 238 is correct. And those are feet squared.
Okay, did you just go wherever just because, or did you need to go to the top, or did you put that triangle down?
I could have done the bases, if I extend them to those parallel lines, the height is the distance between them. The distance between them will always be the same no matter where I measure it at. So I could have measured it down here. It would still be 15 feet. Or 14 feet, sorry. Yeah. I could extend it all the way down here if I want to, and that distance still be 14 feet. One of the definitions of parallel lines is lines that are always the same distance apart. So no matter how far I extend those bases, they're always going to be the same distance apart. So let's take a peek at let's say this is 2 feet by 4 feet. The area that's going to be what? Yeah, 4 feet times 2 feet, or 2 times 4 feet, 8 square feet. By the way, a symbol you might see me put on the board, or you might see at some point in architectural drawings. Of course, that is a square, and that is the symbol for foot. That means square foot. It's an engineering symbol and an architectural symbol, not used as commonly as it used to be anymore. So if you ever see me do that, that just means square feet. Well, let's convert this though to inches. 2 feet is how many inches? Careful. 24 inches. 4 feet would be 48 inches. Well, if I find the area in inches, 24 inches times 48 inches, that is 1,152 square inches. What was our conversion factor to get from feet to inches? Yeah, so if I divide that by 12, do I get 8? I get 96. Why doesn't that work out? Yeah. The 12 is for feet and inches. 2 feet times 12 gave me 24 inches, or 48 inches divided by 12 gives me 4 feet. But this is not feet and inches, it is square feet and square inches. So the conversion changes. The definition of 1 square foot is a square. Yeah, exactly. It's 1 foot by 1 foot. Well, 1 foot is 12 inches by 12 inches. The area of that, 12 inches times 12 inches is 144 square inches. So 1 square foot is 144 square inches. That's our unit of area. So if I want to convert between square feet and square inches, I have to remember that conversion factor. So if I have 1,152 square inches and I want to convert it into square feet, well, I'm going to put square inches on bottom so they cancel out and square feet on top. 1 square foot is how many square inches? 144. And so the square inches cancel out. 152 times 1 square foot, or 1,152, I should say, times 1 square foot is 1,152 square feet. 1 times 144 is 144. We divide that out. 1152 divided by 144 is 8 square feet. So if I have something that let's say that this is 18 inches by 42 inches. I can find that area by doing what? Perfect. 18 times 42 divided by 2 because it's a triangle. So what is that? 369, I believe? 378? Oops. Yeah, you got me there. That's for sure. 378 square inches. Now, if I want that in square feet, what do I have to do? Well, to decide if we have to multiply or divide, that's where it does help to set up these conversion factors. So I'm getting rid of square inches. I'm going to put square inches on bottom, going to square feet. So I put the square inches on bottom so that they'll cancel out. Which one's bigger, a square foot or a square inch? Square feet. So I put the 1 there. How many square inches in a square foot? 144. If you forget that number, it's just 12 times 12. And so 378 times 1 square foot is 378 square feet. 1 times 144 is 144. And then we do have to divide that out. So 378 divided by 144 gives us 2.625 square feet. How about, let's just do this. What if I have 8 square yards and I want to know how many square feet that is? There's 3 feet in a yard, but remember 1 square yard is defined to be a square 1 yard by 1 yard. And so that would be 3 feet by 3 feet. So that area, 3 feet times 3 feet is 9 square feet. So 1 square yard equals 9 square feet. So when I go to convert here, I'll put my 1 square yard on bottom so that they'll cancel out. That's 9 square feet on top. So 8 times 9 square feet is 72 square feet. On bottom is just 1 times 1 here, so that's just 1. So that stays 72 square feet. This is a calculation that's actually done quite a bit in the other direction for flooring, because a lot of your flooring is sold by the square yard. So if I have a room, pretend that's square, that's 12 feet by 21 feet, I find the area by doing what? 12 times 21 oops, 12 feet times 21 feet, which is 252 square feet. Nope, no divided by 2 because it's a rectangle.
Oh, I thought you were trying triangle.
Nope, no triangle there. But now if I want to convert that into yards, square feet on bottom, square yards on top. 1 square yard is how many square feet? 9. So 252 times 1 is 252 square yards. 1 times 9 is 9, so we'll divide by 9. I believe that comes out to what, 28 or something like that? 28 is correct. 28 square yards. When we're talking about area, there's a unit for standard measure that comes into play called the acre. Anybody know how big an acre is? About the size of a football field is about 1 acre, yes. It's 43,560 square feet. Now, where this comes from is we talked a little bit about rods when we're talking about land surveying and stuff like that. A chain is 4 rods. A rod was 16 and a half feet, so 4 times 16 and a half feet makes it 66 feet. So 1 square chain would be 66 by 66, or 4,356 square feet. Remember, we talked about the rod and a chain were our surveying tools when they originally surveyed all the land in this country. That's what they used. Well, an acre was defined to simply be 10 square rods. Or 10 square chains, I should say, not square rods. So, generally, like a city lot is usually 66 feet by 132 feet. That makes it 2 square chains. So that's 1/5 of an acre. Or you can go 132 by 132 for a little bit bigger lot. That's where those sizes come from. It's off of that 66 feet or a chain to get the size of those lots. That's why they seem like really weird dimensions, but that's where they come from. So if I have a piece of land and I measure it out and I get 460 feet on one side and 620 feet on the other side. First of all, the area in feet is going to be found by doing what? Well, 620 feet times 460 feet, which is going to give us, I'm going to use the calculator for that, 285,200. And that is square feet. And if I want to turn that into acres, well, I just put that over 1. And again, I'll put square feet on bottom, acres on top. 1 acre is how many square feet? Make sure you have that number written down somewhere, 43,560. That one is going to get used a little bit in the next couple months. Now, at this point, I think you guys see the pattern. We'd multiply across and then divide out. I'm going to just do a shortcut. Since this number's on bottom, I'm going to divide by it. So 285,200 divided by 43,560, we get 6.55 acres. If we're in the metric system, 1 meter is how many centimeters again? 100. There you go. To get from meters to centimeters is 2 spots to the right. Your decimal point has to move 2 spots to the right. That's 100 centimeters. It's 1,000 millimeters is what you were thinking. 1 square meter is 1 meter by 1 meter. oops, not millimeter, meter, which of course is 100 centimeters by 100 centimeters, giving us an area of 100 centimeters times 100 centimeters, or 10,000 centimeters squared. When we're dealing with metric measurement, what made the conversion so easy was that every spot on the chart was either multiplying or dividing by 10, depending on which direction you moved. Well, if it's area, if it's square meters and square centimeters, every spot on the chart is going to be 10 squared, or what's 10 times 10? 100. When you multiply or divide by 100, the decimal point moves 2 spots. So if we have square units, if this were 4.8 square meters going into centimeters squared, well, we have meters, decimeters, centimeters, and millimeters. To get from meters to centimeters is 2 spots on the chart, but since it's square meters and square centimeters, each spot on the chart is 2 decimal places. So 2 spots on the chart becomes 4 decimal places. So you go 1, have to add zeros, 2, 3, 4. That's 48,000 square centimeters. $570,000 millimeters squared. Does that sound like a big area?
It sounds like, but it's
Not even. If I convert that into meters squared, to get from millimeters to meters, it's 3 spots to the left on the chart, right? But since it's squared, each spot is 2 decimal places, so it's 6 decimal places. You got it. So the decimal starts there. We got to go 6. 1, 2, 3, 4, 5, 6. That is 0.57, just more than half of a square meter. So you're looking closer to the size of the top of this desk. Actually, a little bit smaller than the top of this desk would be that size. That's 570,000 square millimeters. Okay, it's about that time, so let me get some homework out here for you. So our homework for today.
that's homework that I didn't catch up on.
So in the big book, let me make sure I get the right page here. I believe it is page 226 and 227. Exercise 8-5 and 8-6. And also on the big book, page 247 and 248. Exercise 9-5 and 9-7. And in the little book, we're looking at units 21 and 22. So that'll get you guys going. On Monday, I will try to stop a little early, give you guys a little bit more time to catch up on homework. With kind of the weird schedule lately, I realize